Okay, welcome back everyone. So today I'm going to be doing a video on primitive roots, specifically number theory. And the reason being is that I'm planning on making a larger number theory video, which is going to be kind of like a full lecture style video. Obviously these videos are all lecture style videos, but it's going to be a bit more than that. And primitive roots will be a necessity to understand that video. And for this video, well, the primary tool that you're going to need to be familiar with is Euler's theorem and obviously modular arithmetic, but I'm just going to assume that you have a very strong understanding of modular arithmetic at this point. So we're going to use Euler's theorem, and this tool that we proved in the previous number theory video, although we won't be really using it directly, but just an idea to help boost ourselves into what primitive roots are. So what Euler's theorem says, and again I proved this in the previous number theory video, it tells us that for some a to the p minus 1, it's congruent to 1 mod p, where the GCD of a and p is equal to 1. And note that we're working in a mod p, which is a prime. Okay, so, and then this fact here, which again I proved, is the fact that the order of an element a divides p minus 1 mod p. And here's another way of putting that. So we know that, but we kind of want to be, in this video we're interested in the case where the order actually is p minus 1 for some value a. And for what value a does that hold? Well, the values for a where that holds mod p are called g. So g, if g to the p minus 1 is congruent to 1 mod p, and p minus 1 is the order, g is a primitive root. It is a primitive root. Mod p, it will not only have one primitive root, okay? Okay, well, how is this interesting? Well, notice that, well, if this is the smallest value such that this is congruent to 1, then all of the powers of g less than p to the p minus 1 provide a distinct residue mod p. Namely, all the powers, so g to the 0, g to the 1, all the way to g to the p minus 2, this set is equal to the set of all residues, I guess I could just say. So the set of all residues mod p, which is just going to be non-zero residues. So that's just going to be 1, 2 to p minus 1. Just because, well, there are p minus 1 values in the set, and since they're all distinct, they have to equal the set of all residues mod p. Okay? Well, that tells us why we use g as our primitive root. That's because g stands for generator, since it generates all residues, non-zero residues mod p. Okay, so now let's take a look at an example. So we're going to take a look at this example, which is going to be mod 7. And the reason being is we want to consider a different way of viewing multiplication, mod p. And namely, that is as addition. It's the same thing as addition of all residues in mod p minus 1. And to see what I mean is, so let's consider our example, mod 7. And what I'm about to construct might seem kind of arbitrary, but it'll give us a nice little visualization. So it's going to be a kind of a circle. So we're going to have, and I'll tell you that a primitive root mod 7 is 3, because if we consider 3 to the p minus 1, which is just going to be 3 to the 6, you can check that this is congruent to 1 mod 7. Well, it clearly is by Euler's theorem. And you can check that all values less than that, there are no values less than that, such, and the only things you have to check by this little tool here is 1, 3, and 2, and you can check that none of these are primitive roots. None of these are the order of 3 mod 7, and thus 3 is a primitive root mod 7. So we're going to consider the powers of 3 in this kind of circular table thing. So 3 to the 0 outputs a residue of 1, 3 to the 1 outputs a residue of 3, 3 squared outputs a residue of 2, here we have 3 to the 3 outputs a residue of, well, let's see, it should be 6. 3 to the 4, well, let's see, so that should just output a residue of 4, I believe. And 3 to the 5, well, the only one that's not being used, which is just going to be 5. And yeah, you can check that. So that should be correct. Yeah, okay. Because notice that this is just 3 squared times 3 squared, which is 2 times 2, congruent to 2 times 2, which is 4. Okay. Oh, I kind of mixed these up. That might be a bit confusing. So 5 goes on the outside. Okay, so why are we doing this? Well, we're going to use this for 2 facts. I'm going to put this diagonal line, and you'll see why after we consider our first thing. So first, well, let's consider an example. So how can we use this to quickly, well, maybe not as quickly as you would normally do, but to get a different understanding of multiplication mod 7 in this case. But this generalizes, of course. So what is 5 times 4 mod 7? So we want to consider this example. Okay, so to find this, we can use our table. How do we express 5 in terms of the powers of the primitive root? Well, 5, if we go back to our table, we have 3 to the 5. So 3 to the 5, and then 4 is 3 to the 4, which is congruent to 3 to the 9, mod 7. Okay? But notice that 3 to the 9 is on our table. But to get it on our table, we essentially just note that 3 to the 9 by Fermat's little theorem is congruent to, well, 3 to the 7 is congruent to 3, so we're just going to get 3 to the 3. Or another way, perhaps a more direct way of seeing that, is we just take the power and take it mod 7 minus 1, which is 6, and that gives us 3. And that just follows by Fermat's little theorem, by Euler's theorem, that we can make that simplification. So now, notice that 3 to the 3 is on our table. And what does it evaluate to? Well, it gives us 6. And thus, we get 6. Okay? So that's interesting. It might not be helpful computationally wise because we can easily calculate this, but it's a nice tool to conceptually understand how primitive roots help us. But another, perhaps more interesting way to use primitive roots is to find inverses. So what if we want to find the inverse of 2 mod 7? Obviously, that's not too hard to compute without primitive roots, but let's just see what we can do. So how do we write 2 in terms of powers of the primitive root? That's just going to be 3 squared, right? So 2 is congruent to 3 squared. So we want to find a such that 3 squared times a is congruent to 1 mod 7. Okay, well, notice that 3 to the 6 by Euler's theorem is congruent to 1 mod 7. So we just need to find a, all we need to calculate is 3 to the 6 minus 2 is congruent to 3 to the 4 mod 7. Thus, 3 to the 4 is our inverse. And you can simplify that. Okay, well, in general, if we have some residue mod 7, call it a, we can clearly write it as a power of a primitive root mod 7. So we'll call it g to some k power mod p. So to find the inverse of A, well, all we need to compute is, well, following from this idea here, it's just going to be g, so the inverse of A is just going to be g to the, well, 6, that's just p minus 1, minus, well, k here, mod p. And you can check that if you multiply A times this, you just get g to the p minus 1, which is just 1. So that follows. So that's the general form. Okay, so that's really nice. And now, one final thing to analyze, again, it's related to invertibility, and that's which elements are the inverse of themselves. So their inverse is themselves. So the inverse is itself. And notice that, well, we can find a symmetric representation for when this occurs. Because look, if we look at the opposite nodes here, they're inverses of each other by symmetry. Because 3 to the 4 times 3 squared is 1, 3 to the 5 times 3 to the 1 is 1. And notice that implies that the two values on the diagonal are both going to have to be congruent, are both going to be inverses of themselves. You can check that as well. And we want to see, in general, when this occurs. So notice that this actually occurs for the power of g being g to the p minus 1 in general, over 2. Because you can check that, well, p is equal to 7, 7 minus 1 over 3 is just going to be 3, and that corresponds to 3 here. And you can also check that g to the p minus 1 times g to the p minus 1 over 2 is just congruent to, well, if you compute this, you add the powers, you're just going to get g to the p minus 1, which is just going to be congruent to 1 mod p. Okay? So that tells us why this is the case. And to maybe see what this g to the p minus 1 over 2 outputs as a residue, and we'll talk about this as a more general case, which is going to be Euler's criterion in a different bit in the next video, next number theory video. Well, what residue is this again? Well, let's see. So what does it mean for something to be an inverse of itself? Well, that tells us that for some general unit A, residue A times A, it has to be congruent to 1 mod P. But this tells us that A squared has to be congruent to 1 mod P, which tells us that A squared minus 1 has to be congruent to 1 mod P, which tells us that by difference of squares, A plus 1, A minus 1 has to be congruent to 0 mod P. And since P is a prime, either P divides A plus 1 and or P divides A minus 1. And that tells us that either A can be congruent to 1 or negative 1 mod P. Okay? Well, notice that we've already got the one case here checked, because that just corresponds to this here. This is always going to be inverse of itself, 1, 3 to the 0, or g to the 0 in general. So in other words, this value here, g to the p minus 1, always has to be congruent to negative 1 mod p. And that's going to be our final lemma, which we proved, which is the fact that g to the p minus 1 over 2 is always congruent to negative 1 mod p. So that's about all we need to know. There's a lot more that we can talk about, discuss about primitive roots, but that's kind of the general idea, which is necessary to understand our next video, next number 3 video. So I hope you enjoyed this video, and if you want to know more about primitive roots or in general other number theory concepts, please notify me in the comments, and have a nice day. Goodbye.